My name is Attilio Rao, and I think we are in time for the presentation. I would ask sorry for my English because it's not really British English, but I will try to make this a little bit uncomfortable. Better? Okay, thank you. So we are going to speak about the locking infrastructure in the FreeBSD kernel, which is a pretty interesting topic because it's going to be with time very widely discussed on our mailing list, not only from a developer's perspective but even from a user perspective, and we will see why that happened also. In this presentation we will specifically see what was the situation of the first FreeBSD implementations and what changed from then. More specifically, what's called the SMPng era and what we had prior that. We will going to discuss specifically locking primitives that has been introduced with time until now, and problems linked to parallelism in general and how we solve that in the FreeBSD kernel. You can see a table of content a little bit more detailed as listing precisely some problems like priority inheritance and adaptive spinning that we are going to discuss further later. Mostly until FreeBSD4 we had already a multitasking. Sorry, the slide is a little bit confusing, but a multitasking and preemptive system. Synchronization was not very difficult to implement on such systems because if you consider a uniprocessor machine, you can get that the sequential execution was just stopped by preemption and by arrival of interrupts. So you should just maintain consistency of data structures about these two issues. More precisely, we were handling the interrupt synchronizations through a mechanism called SPL. And for kernel threads running in the kernel, we will disabling preemption in order to avoid the corrupting of data structure. This approach, while was pretty good on uniprocessor machines, was actually impracticable for the SMP environments. More precisely, because we had more cores that was running a thread per time, and so parallel accesses to the data structures were still possible. In order to avoid big problems in the kernel, we had to just allow the entering of one thread per time in the kernel. While that was a pretty good approach for workloads that were mainly in user space, for workloads requiring a lot of I/O, for example, they were wasteful because they wasn't getting any advantage from the new SMP architectures. Like the parallelism was basically zero, at least in the kernel. In order to fix that, a new project was created called SMP New Generation, or the NG. As you can see from the slide, the entering in the kernel was prevented by using a big lock called BKL, basically. With the FreeBSD5 we had the SMP New Generation project. Basically it was a sanitization of all our kernel and a re-engineering of a lot of mechanisms inside our kernel. We could see it FreeBSD4 and FreeBSD5 as mainly two different kernels because substantial subsystems were rewritten and were rewritten with the idea to use and implement a real parallelism in mind. we can say that basically it was a major task, a very big task, and that it required a lot of years to be brought in a good shape, at least. In Italy, people gave a lot of complaining about the unrobustness of the FreeBSD 5, but probably that's because they couldn't even see that the changes were really, really important and really, really huge. However, for FreeBSD 5, based its initial SMP system, inheriting from the BSD-OS, that kindly released this code about that, and the process was break up in some precise tasks, at least in Italy. Mainly, the first things was introducing in the kernel a new set of atomic instruction and locking primitives. Then introducing an abstraction called interrupt threads that we are going to discuss better later, but it was basically restructuring completely the interrupt mechanism that was in the FreeBSD 4. The BKL lock was moved to a real mutex called Giant that still exists in our kernel, and there were introduced some threading primitives like M and ON threading primitives called also keys SC, which are actually never used in our kernel, and they have been exited out, I think, the past year. And slowly, the porting of all the relevant subsystem to a final locking was started. I have to say this task is not still completed, it's still going on, but we are in really good shape about that. Just few subsystems remain which are still Giant protected, and with the new release that we are going to ship this year, I think that we made a very huge step forward in this direction. Really, the SMPng has been considered closing around the end of the 2007, but the important parts were these initial moving. Another thing that's not listed here, but I can tell you is that even that if Giant was preventing any parallelism, initial parallelism, there were imported new kernel memory allocator that was scalar, and the scheduler was moved to a separate lock in order to start getting a little bit of concurrency, of real concurrency. Before to speak about FreeBSD specifics, we can start digging about what kind of locking primitives you can find in our kernel from a more historical point of view. We have some versions of mutex, which I assume people here knows about that, but I'm going to give a little explanation for people that doesn't know. A mutex is basically a lock allowing to access to some protected data structure just one thread per time. So if a thread owns the lock, owns the mutex, other threads won't be able to access the data structure until this lock is released. We offer even some kind of locks called RW lock, read-write lock, which are basically locks that can be acquired in two different versions. One version is the write lock, which is the same as a mutex, just one in the protected path per time, and another one is the read mode, which basically allows all the thread willing to acquire it in read mode to concurrently access to the structure, but prevents the writers from accessing to the protected path while there are readers. Then we have even locks called the read mostly, which are basically the same of read-writer locks, but they have some optimization in order to make the read path really fast and to have like a zero overhead kind of lock from the read path, while probably the write path is even heavier than the other one. But if you think about cases that just where there are a lot of read chassis and very few write chassis, you can find that a very useful primitive. Then we have some form of weight channels. Weight channels basically are a generalization of what other people can call like condition variable, and they basically let a thread sleep under some conditions that are previously set with some variables. Usually, having a weight channel means that its chassis are controlled through another locking primitive like a mutex or an RW lock, and so often a weight channel is associated to its locking primitive. Usually, if you have no necessity to use a weight channel without a locking primitive, you probably have a bogus code. But there are some edge cases where that is even possible. As last thing, FreeBSD support even counting semaphore, even if that's considered an old feature, as we are going to see, and its usage is pretty much discouraged. Basically, in FreeBSD, you can consider locking primitive divided into three classes of locking, based mainly, in particular, from an outside perspective, based on the behavior the contending thread have in regard of the lock. For example, in the case of a mutex, you can get that spinning and blocking mutex do very different things about the contenders, as we are going to see more precisely later. Usually in the traditional literature there are just two cases of the lock classes mainly. You will find the spinning lock and the blocking lock, or they call often sleeping lock. I think that as we are going to see why we have three types, I think that things will be clearer. But if you have any questions, please ask. That's not a problem. Spinning primitives, as I told you, allows the contesting thread to check the status of the lock periodically, and they just do busy waiting around the locking variable. As a spinning primitive, FreeBSD just offers mutex. What are the problems linked with this class of locks? Mainly, it's that CPU remains busy without doing really nothing useful. It happens that if several threads contest on the locks, basically they share the same cache line where the lock is. That means that sharing a cache line means a lot of underlying activity on a lot of architectures, like, for example, having a lot of snoop messages between CPUs and some buses traffic, which means in very heavy operations. And the last thing is even the most important you can notice there is that interrupts are disabled while spin locks are held. That happens mainly because there were identified in the past some kind of deadlocks possible if you were going to leave the spin locks, the interrupts enabled while holding a spin locks. In particular, you could find that there are some problems with the interrupts handling code in the bottom half that was going to deadlock. It's not very simple to understand, I think, so I've left out. But if you want to know, we can speak later, probably. With spinning primitive, we have even blocking primitives. Blocking primitives allows basically the contenders to be scheduled from the rank queue to be put on another kind of container. And basically context switch immediately. They will put again on the rank queue of the scheduler just when the owner is going to release the lock. and it will be the owner that was going to have the load to make all the handover operations about that. We have several primitives implemented as blocking primitives, like mutexes, RWLocks, and RMLocks. Basically with the blocking primitives, we have a lot of advantages over the spin mutex, like having the contenders that sleeps or that blocks, avoids CPU biasness, and mainly we can leave basically the interrupts allowed. That happens mainly because the interrupts code is just allowed, at least the bottom of one is just allowed to use spin locks. Probably if it was going to use blocking primitives, we would have even to disable interrupts here. There are, however, some big drawbacks that, as you will see, we handle in FreeBSD in order to make the blocking primitives our how could I tell, the first choice in terms of locking. We have a problem called priority inversion, and we have the problem that context switches are very heavy, in particular on machines that FreeBSD uses as referral, like E388 and MD64. But as you are going to see, we use two techniques in order to cope with that. Another thing is that while you can't allow context switches while holding a spin lock, it's obvious you can't acquire a blocking primitive while holding a spin lock. That's an important rule in FreeBSD. That sometimes it's confused and often it's not observed. That leads to bug, obviously. Usually you would always prefer a blocking primitive to a spin lock, if not in some very particular condition, like what I already said about the interrupt, and even about the some paths that are very, very short. We should have some example in the kernel, even if I can tell you one right now. I have no idea, actually. Said that, we are going to see problems linked with the blocking primitives. The first one is called priority inversion. Basically, it could happen that like a thread D, which has a priority, owns a lock called L, for example. Then another thread with an higher priority than the first one locks on this lock. What happens is that the second thread, the thread B, for example, will need to wait for a lower priority thread to finish its workload. We solve this problem actually in the kernel using a technique called priority propagation. Basically, what happens is that priority of thread B, the higher, is lent to the thread D until it doesn't release the lock. It's directly implemented in the container, the turnstiles. While that could be done even on the primitive, it has been much convenient to use the container for that, because it was going to offer some advantage we are going to see right now. Just note that deadlocks cannot support priority propagation fixes for deadlock. That happens because you would like to the turnstile should keep track of all the readers, and this would be very, very expensive from a point of view of the overhead. And even I think that I tried to do something in this regard, and I saw that there were some races that were requiring to acquire a spin lock as base even in fast paths. So it was an impracticable way, I will tell, at least for what we found so far. Basically, what happens about the priority propagation is that the threads and the turnstiles are chained together. The thread owns a pointer to the eventual turnstile it's sleeping on, and the turnstile owns a pointer about the owner of the lock. What happens is that, for example, in this case, we have a sleeper which is going to sleep on a turnstile, the first one, which has a priority of 128. The turnstile, through the pointer TS owner, knows which is its owner, and this owner has a priority of 256. As you know, higher values means lower priority. So this is a suitable case for priority propagation. But what happens is that this owner is actually sleeping on another turnstile, and the other owner of the second turnstile has always the same priority of its sleepers. So just propagating priority to the first owner was just unuseful, because the first one could still keep the chain to a lower priority. So it was going to be propagated to the first one actually running owner of the chain. This is the situation after the propagation. As you can see, all the threads in the chain has the same priority, the higher possible. In this case, the one of the last one arriving. There are questions about that? No?
The priority will go back to what it was before, after they...
Yeah, when the for example, the third owner, right, the second owner there, when it goes to release the lock, it basically brings back the priority to the 2065, to all the chains he is responsible for. So it just happens at unlocking operation. And that's what we do about the priority inversion. In order to fix instead the overhead given by a big amount of context switch, we use another technique called adaptive spinning. Basically, as a context switch brings a lot of overhead, we prefer to not do completely a context switch in the case the lock owner is still running on a run queue, because there are very good chance that the owner is going to release the lock very early. That means that, for example, we choose just to spin in order to wait that the state of the lock had changed, or the state of the owner was going to change, like the owner going to sleep on another turnstile. And basically, there have been very big measurements, even in on other operating systems like Solaris, that where I think we brought in this approach the first time, that were showing a very big improvements in performance from this technique. Apart from the two types of primitives we already saw, there are sleeping primitives. Now there is a consideration we have to make about that. Basically, sleeping primitives should be, in theory, just the wait channels. The wait channels should have been just the only one implemented using a container called sleep queue. But due to some legacy, actually the sleep queues were used even to implement other kinds of lock, like the lock MGR and the S6 locks, and basically the semaphores countered too. That has been this is going to give some problems actually, because as we are going to see, and as you can see underlined too, in FreeBSD, while sleeping, threads should not hold any kind of lock, neither blocking or spinning. That's a simple thing to explain. We just want to enforce correct semantics of locking. So imagine to keep a lock a blocking primitive while sleeping. It's going to waste a lot of time because all the contenders are going to start on the lock owner which is sleeping. Basically, in fact, what, as you should know, condition variables do usually is to drop the lock once it's passed to the primitives. In this case, basically, we just don't allow that. This means that the same conditions happens even for other kinds of lock, the lock MGR and the S6 lock. So you can hold a mutex, for example, a blocking mutex, an RW lock, while trying to acquire a lock MGR on AX6. This is going to create some problems because in some paths that's unavoidable. So you have to drop the lock, for example, and try to acquire the other primitive, which is going to break the protected path and so can create some race problems. As the sleep queues are born just to serve wait channels, they don't track owner at all. So they don't care about priority propagation and priority inversion problem. Just because sleep queues in theory should not have a nowhere. So, for example, lock MGR and S6 have not priority propagation systems, and they are discouraged to be used even for this thing mainly. Sure.
I want to know the benefit of sleeping primitives.
Well,
very bad primitives.
You mean why doesn't the blocking primitives exist? Yeah. So imagine that, for example, you have a wait channel, a convar, a condition variable, or a msleep. Msleep, the primitive that allows you to sleep on a condition variable, for example. However, you are using the blocking, using the turnstiles. You would go to have always the mechanism of priority propagation and priority inversion handling. It's not very, it's pretty heavy. It's not a simple operation. It acquires even some internal spin locks in order to avoid some races, and so it has an overhead. If you do, in this case, it would not be useful. It would be completely unuseful to have a mechanism like that. So, in theory, if you just would have used the sleep queue for wait channels, you were going to have a big performance boost than just using the turnstile for the same problem. In theory, but what happened is that other locks are implemented using sleep queue. That should have not been happened on the principle. Really, I'm not sure who introduced the S6 lock. I'm actually not sure. And even lock MGR. But, however, as you could have seen before, the three containers create a hierarchy that should not be broken. Like, you have spin queues, you have spin locks, you have blocking primitives and sleeping primitives, and you cannot mix them. There are precise rules, like on the top the sleep primitive, in the middle the blocking primitive, and in the end the spinning primitive. The main choice would be just to use blocking primitives always, because as you can see, we handled a lot of problems that they have, and in practice they have proven to be very, very helpful. But sometimes some nasty conditions can happen. For example, one of the most widespread is using malloc with the flag mwait OK. In FreeBSD, that means that if the allocator is pretty busy, you are going to sleep in order to retrieve your memory. And if you do with a lock hold, you are going to violate one of our rules, and it's not possible. Or another one is we just said before, like call a sleeping lock while holding a blocking primitive. In the next example, I'm going to show you a way to handle, for example, with the malloc case and similar. But usually usually that are not very common cases, at least for simple paths. You should even try to avoid yes, even in the weight channels, as in FreeBSD, you can differentiate between condition variables and msleep. Usually msleep was introduced as the first primitive, but it has an interface very difficult to make saner and to understand, at least for people which are comfortable with the interface of condition variable that we also support, but they are a newer primitive. Mainly there is so for the newer code, what you should do is just to use condition variables and not msleep. Basically, msleep should be dropped off, but they have a very nice feature, which is the possibility to specify a wake up priority on the sleeping threads once they are asleep. That Convar still doesn't have. Maybe if we could port these features to the condition variables, we will be able to completely drop off msleep from our kernel. This is a simple case that it's going to show a way to a simple way to deal with the, for example, condition I told before, the malloc willing to sleep, and doing that while holding a lock. As you see, we have a sucked fake C that has some members like flags and an object called sucked foo, which needs to be allocated, and they are protected by an internal lock. You imagine that, for example, the fake C create holds the lock of the object and does some things which are not important. Then, in the end, for example, it's going to allocate the FC object, and that should be protected in an atomic path. Something you can do is just to set a flag for that, saying the allocation is going to happen. If you access to this structure concurrently, just skip the allocation. And that's what we do. We check for this flag, and if it's present, it means that another thread is already allocating, and we just skip. Otherwise, we set it, and then we unlock the mutex. Then we allocate the memory for the object, acquire again the lock, and we simply assign. Please note that I've used a temporary storage for that in order to make some assertion, like the MPass, about the pointer. It was just a trick in order to verify that really the structure was not already allocated, and so that we can get some kind of assertion about that. One of the biggest innovation that was brought in FreeBSD, apart the locking primitives, are the interrupts thread. Mainly, this is pretty simple to explain. Maybe, as the top half remains basically the same, and was going to handle the ESR for the interrupt line, for example, the bottom half changed. Instead than running the interrupt handler installed on that line as it was traditionally happen, it was going just to schedule a thread that was going to run the interrupt handler in a precise context, and not the kernel one as it was going to happen traditionally on a lot of Unix system. This has the big advantage that using your own context, you can basically you are not forced to use spin locks, and you can do a lot of other fancy things. This necessity came over because often interrupts handlers needs to access to some subsystem locks, and as we were going to use blocking primitives all around, we would add the necessity to support the locking of the possibility to acquire mutex actually. A similar thing was implemented using task queues previously, and sometimes I think I saw on Linux too using tasklets maybe, but it was basically something similar, but not exactly in this way. Actually, in FreeBSD, in particular from the release 7, the interrupt threads this model is a little bit changed in order to include a new mechanism called filtering. We have interrupt filters that basically instead than directly schedule the thread linked to the hierarchy line, they just check for they just let run some routine in the kernel context that will decide if handle directly the request or just schedule the kernel. It's like if you have the old bottom handler that had the possibility to register an handler still running in interrupt context, and at the same time decide if schedule a thread or not, so that it's no more mandatory. So I think that the first part is going to finish, so if you have some questions we can handle right now. This should be material for the second part actually.
I have a question. Go ahead.
What are the remaining parts in the kernel that are still under giant?
New bus, for example, some drivers that are not frequently used. I'm not sure which ones, but all the big ones are converted to finer locking. Actually, the problem is not which parts are under giant. It's how we could optimize the locking of some subsystem, because, for example, we have the virtual memory, which is not under giant, but it's not locked optimally, and it's going to bring a lot of contention. So it's not under giant, but it should be optimized. Because the parts under giant are very teeny. I remind the new bus, for example, and some parts relating to the VFS on the mounting and unmounting, but they are very short parts. Not sure about others.
My question was going also in that direction. Will giant, the idea of giant was to push it out all the way and to actually not have it anymore, but it probably will always stay.
Sorry,
Giant will probably always stay for certain parts.
Well, ideally it should be removed completely.
That's the plan, but my question is, do you think it will ever happen?
Yeah, sure.
Okay.
It could happen.
Now, the second question is, are there tools to optimize locking? Because you actually just, in answering this question, said it's sometimes difficult to do the locking in the right way. Because you're working in some routine, you do your locks, you find you're doing it correctly, but in the bigger picture, those locks actually are not optimal.
Okay, yeah. Allora, in the kernel we have basically, as you should know, we already imported dtrace, for example, and I have submitted by a developer, I can't recall right now, some patches that brings the dtrace hooks directly in our locking in order to allow it to be tracked with the dtrace. Which is very nice, but it's still not committed.
Okay.
We are reviewing. About that, we have a very useful tool called lock profiling that has been very helpful in the past in order to find the most content of the lock and to try to decompose them to finer locking. Mm-hmm. So at least for the kernel, we have such a mechanism. I'm not sure what should have in the user space. I'm sure we have not something similar, but for maybe other systems have similar tools. I don't know. I just follow FreeBSD. So
I have a question. On the uniprocessor, do some of this stuff become much simpler? like kind of automatically, because there's a lot of overhead to lock things, right?
Mm-hmm.
And if you don't need to do it because you're on a uniprocessor, then maybe you can skip that stuff. Is there anything like that? Maybe the macros don't, when you compile for a uniprocessor, it does less work.
Not sure. Could you repeat some voice, please? Because no, I can't hear.
It seems to me that you don't have to do all the work that you do with locking if you're not on SMP, right?
Well, no, it's not right, because you have to protect even against some mechanism like preemption, which is going to be tricky. It's different implemented than the FreeBSD4. So it's going to be with preemption. It's like from it's like if you have a real SMP system from a technical point of view. So you have to handle problems typical of that. Really, in the kernel, we have other kind of synchronization, like atomics. I thought I should have had a slide about that, but it disappeared. So I can tell you by voice. We have the possibility to use atomic instruction in FreeBSD kernel directly, but and to use even memory barriers linked with them. The only pitfall is that you cannot really trust about case coherency, because as long as it's MD specific, you can just be trusty about what happens on your CPU, where you use the atomic and where you use the memory barrier. You cannot make assumption about what happens, or if other CPUs can see your modifiers or not, and if the cache can handle that. We have specific primitives in order to, for example, disable preemption, which are the critical sections, critical enter and critical exit. That while you call them, you are not. The preemption is simply disallowed. That's a very fast primitive, so there is no much overhead. There is not much overhead. We also have a way to disable interrupts, which is unofficial. I will tell you that because you can do that in a machine-dependent way with the spin lock enter and spin lock exit, and then you can even disable some thread migration using the scad-pin and scad-unpin primitives. That are very useful when you are going to access, for example, to per CPU data, and you have several chassis, and you don't want the CPU migrate from that the thread migrate from that CPU, because you could read different values on different CPU. Then I'm not sure if there is something else. Okay. Questions? No? So see you later.